Hi, I'm Eric Gore, Technical Director here at CSI. Thank you very much for joining us in our virtual PAC Expo. Today we're going to be demonstrating some typical process problems. So mostly focused around water hammer, and then I know our time's kind of short. We get to it, we're going to cover a little bit on tank cleaning. Hopefully share with you what causes some of the problems, some ways to fix it, and just give you some good information. With me today, I have John Riley, one of our business development folks from California. Before I turn it over to him though, I want to share with you a little bit about CSI if you're not familiar. So we engineer, design, and build process systems similar to what you see behind me, as well as we're a stocking distributor of all the process components inside of these systems. So pumps, valves, heat exchangers, things of that nature. One last thing before I turn it over to John, feel free to put questions in the chat log. We will be monitoring that. We'll answer your questions live as they come in. If we don't get to you before the end of the presentation, we'll circle back around with you shortly after. Again, thank you for joining us. And John?
Perfect, thank you, Eric. Well, common issues, like Eric said, is water hammer. And so we're gonna talk about it first, and then we're gonna show it to you on our test skid, our simulated skid here, and give you an idea of what it's about. But first, we need to talk about water. And it's really easy to forget that we only carry around a few ounces of water and we don't realize how heavy it is. But in a process skid like this, it carries a bit of mass. And so when all that water is moving, it's got a lot of momentum flowing through it. If you look at the skid, you probably got about 170 pounds, which is equivalent to what Eric weighs. You'd have to add a few more lines of hold tube there to get my weight. But if you suddenly stop this skid with all that momentum running through there, whether it's 50 gallons a minute or 100 gallons a minute, it's got a lot of momentum to stop. And water's not compressible or springy. You might as well be slamming concrete or, through it into the valves and into the tubing. And instead of being absorbed, that sudden change in momentum creates a spike in pressure, and it travels as a shock wave through the entire system. Commonly, this pressure spike, it can be 5 times the static water pressure in the system. Often, that shock wave is gonna make some noise and you're gonna hear it, and that's water hammer. So imagine if you're an operator and you're at the end of a line and you shut down a valve and you slam it closed quickly. That is the equivalent of me running into a wall. And that pressure spike can, and that change of momentum that it causes, it can cause some serious damage within the system. So I think next we should look at what that looks like. So we're gonna look at our test skid here. We've got a tank. It runs down to the valve, to the gauges. It goes through an Alfa Laval L-cage pump. It comes up through here and it runs all the way through the hold tube. We're gonna focus on this area, but after it passes through the valve and this pressure gauge, it goes back and returns to the tank. So Eric, let's go ahead and look at this right now and what water hammer actually looks like. What are we running at pressure hertz?
We're running the pump at 10 hertz, which is giving you about 25 gallons a minute.
Okay. So we got about 25 gallons a minute. If we go ahead and slam this valve shut, it's at the end of the line. You're gonna hear a little bit of a noise and you're gonna be able to see this pressure gauge jump. So I'm gonna let it run a little bit. Focus now on the pressure gauge and we're gonna watch it, and you can see how that pressure gauge gets jarred and the whole system does. Now Eric, if we turn it up just a little bit, what does that look like?
So we'll do 15 hertz, and that's gonna give you about 55 gallons a minute.
Okay, so 55 gallons per minute.
You about doubled your flow rate.
We've doubled the flow rate, but still running at a very low range for that pump, right? You said 20%?
25%.
25%. So now if I close this quickly, you're gonna be able to hear it. You can see the whole skid shake. And now if we focus on this pressure gauge, that kind of jumped between what I think it was like under 5 PSI on the last one. If we do it this time, it hits up to the 20 PSI, and you can see that whole system shake and make a loud noise. And so Eric, as I'm thinking about this, what kind of damage have you seen? You've been in a lot of plants. What kind of damage have you seen?
It can be really violent. I'd say the extreme cases, I've seen it yank pipe around so much it actually ripped hangers loose from the wall that was holding the piping up.
Yeah.
If you have escutcheons where you're passing piping through the wall, it generally knocks them loose if they're just glued on. In the system itself, it's really hard on pump seals. I've seen it damage pump seals as that shock wave worked its way through the system. And then I've seen tri-clamp gaskets actually shot and stretched out from 2 ferrule faces.
Yeah.
I've seen butterfly valves, so similar valves to this, where the elastomer, the rubber parts, were stretched out down line. And then also in some extreme cases, I've seen it actually bend stainless parts. So in a butterfly valve, the butterfly itself actually bend and change shape.
Wow.
And then seat valves, I've seen them where the stems were maybe bent or damaged as a result of it. Cracked bodies, things of that nature.
Yeah, so it can do quite a bit of damage, and then, so obviously we want to prevent that. Best ways to prevent the water hammer.
Yeah, so there's a couple of things you can do to prevent it. One is if it's manual valves like this, where an operator's going to do it, is just train them. You don't have to do everything in a big hurry. So you heard how violent that was when you shut it.
Yeah.
I'll do it slow and listen to the difference.
Yeah, there's a big difference.
Really a non-event. So train people to close valves slow. That's also true if it's a controlled system. Make sure that your valves close slower. Yeah. And there's ways to control that. Some other things that cause water hammer in a system is wrong valve selection and or installation. So a lot of pipe fitters don't necessarily appreciate that a valve has an in and an out in some cases. Some valves, like butterfly valves, just inherently are going to cause water hammer. So good valve selection, good training with your pipe fitters can help eliminate and prevent water hammer. Then if you can't stop it due to valve issues, a good trick that I've seen people do, if it's a controlled system, they might program the pump to pause for a minute, just let the valve shift, and then turn the pump back on, help eliminate water hammer.
Yeah.
That's some things that I've seen.
No, makes sense. Well, I'm thinking that we've hammered on this
System quite a bit.
We should probably move on to tank cleaning.
Okay.
So, as we're looking at tank cleaning, and Eric's going to switch it over now, so the flow is going to be going through the spray device. Obviously, the main goal of cleaning a tank is to be able to clean the whole tank. So, as you're looking at this spray system, we have a rotary spray ball here. Tank companies, distributors, they can help size a proper spray ball to fit your need and your application. However, just because you get the right spray ball doesn't mean that you're always going to have success. There's an optimal range of pressure that's required to operate the spray device, and for this device, for instance, it's 22 to 44 psi. However, if it's too long or too short, too short or not enough pressure or too much pressure, you can also have adverse effects, and we'll cover those later on. But right now, to look at something what we're running at, 8 psi, you can see that we're not meeting the optimal range of 22 psi, and we're missing spots in here. We've got cascading down the side here, which is what you want, but you can still see all the areas that aren't getting cleaned. So if we go ahead and turn that up, Eric, to let's go to the minimal range. So now we're at that 22 psi where you can see it's getting that full sheeting now. It's even at the minimal requirement. So you can see you're getting all that. If we go to that next range, which is the optimal, the ideal, kind of in that center, between the 22 and the 44, you can see it even gets a little more agitation going on in there. You're getting a lot of cascading on there. And then Eric, if we go all the way up to that top range, the maximum, you can see how violent it gets in there. It's really throwing a lot of water around, getting a lot of clean. So it's gonna knock off any debris that we have inside the tank. So, and then we can't demonstrate it here, but if we did get up and we had like a static spray ball in there, if you were to over pressurize that pump and get it and get that flow going too much, you would actually atomize the water and it would be a mist inside of that tank, and you wouldn't get any cleaning down the sidewalls as well. So, Eric, I know in some of the applications we've talked about, what have you seen where people make mistakes in putting a spray ball in aside from pressure?
Yeah, some other problems I've seen with tank cleaning issues, even if you have the right device, you're able to give it the right pressure and flow, some other things I've seen result in poor cleaning is maybe the device is just in the wrong spot. So it might be too high or too low, generally too high being the problem. Or if there's features in the tank that might block that water from hitting the side, we call that shadowing. So maybe there's an agitator blade or baffles or something that prevent you from being able to hit the entire tank. So in that instance, then you might need to have 2 spray devices or multiple spray devices rather than just one. Well, folks, thank you very much for joining us. Hopefully you got some good information out of this. Some ideas that will maybe help you uncover problems in your facility and or do a better job cleaning tanks. We're here to help you. We've got some questions that are coming in on the chat, so we'll try to address them. Meantime, if you think of something you want to know more about, please put it in there. And again, thank you for joining us at PAC Expo this year.
Before we get to your questions, just want to let you know we're going to try to get to all the questions that we have on the board, and if we don't get to your questions, please, we'll reach out to you, and if you have any other questions that you didn't get a chance to enter, please go ahead and call us and let us know, Eric and I. Eric, I noticed the first question. So Eric, is there a rule of thumb when setting up a valve manifold, like open close sequence, to avoid water hammer?
I don't know if there's necessarily a rule of thumb, but there are some just good practices. If you're going to close a valve, if you can, open another path, meaning as you schedule a valve to close, just ahead of that have another valve that's going to open. That way the liquid always has a path. That will help prevent water hammer.
Well, so now in thinking about that, is there a way to change the speed of when a valve closes and opens? Like, can you adjust that speed?
You can a little bit. That's more about controlling the pneumatics or the air that's opening and closing that valve. Some ways that I've seen people do that is they might put a needle valve to you go to your normal pneumatic supply house. I'll know what you're looking for, but you put a needle valve on there and control the speed at which it opens and closes the valve.
That makes sense.
And that can help eliminate water hammer. Similar to in the demonstration, we closed it slowly, and you notice that you don't get that hammer.
Gotcha.
So you can do that.
That makes sense. So Eric, as you change the pressure feeding spray ball, does it change the water consumption? I'm assuming I know the answer to this, but...
It does, but not as dramatically as people would presume. So
Yeah.
you think of the spray device that we happen to have in this vessel, it was 20 to 40 PSI is its optimal range. If you go look at the pressure curve on that device, the amount of gallons per minute used between the low pressure and the high pressure on is just a few gallons a minute difference. It's really not that dramatic.
Okay, so next question, Eric. It looks like during the demonstration, we noticed the tank has water in it. How much water do you recommend be left in the tank for cleaning? And I think this is we had a similar question to this in our pump cavitation discussion where we talked about...
We did. In that
levels
demonstration,
there.
we talked about this same concept. So in this instance, this demonstration, we have water left in the tank because it's a closed loop. Water is recirculating back into the tank. In an ideal situation, when you're CIPing a tank, you want the tank fully evacuated. So you want that liquid to cascade down the sidewalls, clean the bottom head, and go out the drain. If you leave level in the tank like this, you're very prone to have longer rinse cycles. It just takes longer to rinse the debris or the chemical out of the tank. And you'll see a scum line a lot of times, like a ring, where that level is left.
Makes sense.
For CIPing. Now there are times when people will purposely build some level in a tank. Let's say example, if you happen to have some agitators, it's hard to clean the bottom side of those agitators from a spray device. So you let enough water come up on them that as they spin, they clean themselves, and then you evacuate.
Thank you guys for joining us. That's all that we have time for. If you have any other questions that you didn't get to, please feel free to call Eric or I, and let us know if you have any other questions. Also, Eric's going to be doing a pipe tight demonstration tomorrow, same time, 11:15, and so please tune in and hear what he has to say about that. Anything else, Eric?
No, thank you for joining us.
Thank you guys.